Jean in the seminar, but also for other occasions, conferences, and so on. So Jean will tell us today about phenotype divergence and cooperation in isogenic multicellularity and in cancer. Please, Jean.
Thank you, Vitaly. Привет всем. Hello to everybody. So it's my pleasure to thank Vitaly and all the organizers of this meeting, remote meeting. And indeed, I will try to present to you my ideas and work with Frank Ernesto Alvarez Borges, who is just a fresh PhD titular from Paris Dauphine University and Havana in Cuba, about this work that we have designed together. So it's about biology of multicellularity and of cancer, because as you will see, cancer always starts again a new try in multicellularity, but of course tumors fail because they lack control on cohesive multicellularity. This is the main idea, and I will try to present you a small ingredient of the construction, the design of multicellularity, and what cancer in tumors is trying to do unsuccessfully, and which is phenotype divergence. Indeed, in development, in early development, cell lines have to diverge by phenotype specialization to design cell lines. And this starts in an isogenic environment that is starting from a unique cell, which is a zygote or fecundated egg in multicellular animals, which is the only way, the only species that are concerned by cancer. So let me start. Please, next slide. So in my talk, I will present to you isogenic multicellularity cancer, and what is also a way to understand it better, the atavistic theory of cancer, very briefly. I will also present you, and this will be after the biological part, the main model about phenotype divergence, which we designed with Frank, with reaction, diffusion, and advection equations, PDEs. Then also with Frank, we have tried, and this will be a paper that has been submitted and presently in minor revision, and which should be very soon published, a way to present cooperation, because what we have thought with Frank is that just thinking about phenotype divergence is not enough, because as you will see in the last slides, giving sense to separation and distribution of work in the construction of multicellularity makes more sense when you include cooperation. So it should be phenotype divergence induced by in enhancing cooperation between cell lines. And this will be done first by a discrete model, and then starting from this discrete model, by analogy, a toy model by using PDEs, which has been completely designed by Frank Ernesto Alvarez Borges. And this is now underway. This is in progress, and this hopefully will be the object of some upcoming PhD thesis. So next slide, please. Yes. So what is physiological multicellularity? It is a mandatory framework to consider when one tries to understand and fight cancer, because cancer is a disease of multicellular animals only. And unfortunately, many biologists of cancer are focusing only on the single cell and not taking account of the tumor environment and of, more generally, the fact that multicellularity is, as I say, a daring physiological construction from the zygote, but it is the setting in which cancer develops. So no multicellularity, no cancer. But in physiology, there is a strict control of cohesion of all its cell constituents, and this is what is lost in cancer. And what is at the foreground of cancer is cell plasticity. It is physiological in early development, and it is of epigenetic nature. It is maybe considered as a cellular trait in development, but it cannot be kept in cells in an achieved multicellular organism, lest the organism be in permanent danger of losing its cohesion. So plasticity is at the beginning of the design by the body plan, as you will see, of any multicellular animal, but it must be forsaken for the benefit, for the sake of cohesion in physiological multicellular animals. And this is stored, this construction is stored in the body plan, which is not only anatomical, but also physiological. And it is a program of construction of the species of any animal in each species, and it is the object of what evolution, Darwinian evolution, works on. And in cancer, as it relies on control of physiological control of differentiations and proliferations, mainly of differentiations, I insist on this. In cancer, this is lost, and so plasticity is at the foreground, and cell specializations may occur, but compatibility and cooperativity also, but it is lost in cancer. The coherence of it all is lost in cancer. And so next slide, please. And yes, as I was mentioning previously, the body plan is a program of construction of multicellular animal, and it may be considered in a metaphor which I call the wicker-work basket as a fiber bundle. I have not found so far the perfect construction from the differential topology or differential geometry point of view, but I think that it must be possible to design it. And so cell lines are between cell differentiation trees, and between fiber connections ensure the cohesion of the whole. So it's like designing a wicker basket, and you need not only the cell lines, which are the fibers, starting and setting from the zygote, the first fecundated egg, but also you need between a fiber connection solidization, if I may say, cohesion, which I call the cohesion watch. And in cancer, this cohesion watch, that is the cohesion between fiber connections, are lost. This is a metaphor. Another metaphor, next slide, please, is, I will see it after. This is the best known case in normal development, hematopoiesis, which is the way by which you can see the design of such trees. And so stemming from one cell and secondary tissue stem cells that go on building the construction of the multicellular animal. Next slide, please. And this is a generalization put forth by from the Wellington epigenetic landscape by Tariq and Ver at an American Society of Hematology meeting more than 12 years ago. Next slide, please. And in the two settings, Darwinian evolution and development, we will see that this is a way of how ontogeny recapitulates phylogeny. In a billion-year perspective of Darwinian evolution of animal species, that is, of body plans, phenotype divergence was also present, but it was fixed by mutations in what has become the tree of life in the Darwinian evolution perception, the perspective. So, but in multicellular development from the egg in a given animal, it's not fixed. At least it's not fixed in a irreversible way, starting from the zygote, but with epigenetic phenotype divergence resulting from its successful cooperations. It's a perfectly deterministic process opposed to the more or less stochastic process in the Darwinian evolution of species. And this is the way, in my mind, where one can understand ontogeny recapitulate phylogeny. So ontogeny is perfectly deterministic. It's contained in the body plan, whereas phylogeny has been encompassed with changes in the environment which have induced phylogeny. And from the point of view of this epigenetic phenotype divergence, which is the basis of the body plan, cancer alters the maintenance of this anatomically and physiologically unfolded body plan, which is maintained by connections between gene regulatory networks that make its cohesion. And it should be a very important way to develop in investigated gene regulatory networks to find how they are connected together by messages not unfolded generally to ensure this local cohesion. And this is a way, according to my point of view, by which cancer begins. This is by losing these cohesion principles between gene regulatory networks in tissues or in individual cells and tissues. But in cancer, tumor cells, which are a sort of beginning again multicellularity, tumor cells keep their genome facilities that remain in the program of their body plan, but in an incoherent way, and they have the capacity to develop specialization and possibly bet hedging, and possibly also intratumor cooperations, which are inherited from their evolutionary past as they have acquired uncontrolled plasticity and can resort to every possible capacity that has been stored in their body plan program with the acquisition of mechanisms of defense found in the evolution of the species. The next slide, please. And this way is perfectly, how should I say, illustrated and documented by the atavistic theory of cancer, which provides us with a vision of cancer as a regression towards a coarse, unachieved, and plastic form of multicellularity. This has been documented until very recently by, of course, firstly, the Princeps article of Davis Lineweaver in physiological biology, but until recently also, not only by Davis and Lineweaver, but by investigating paleogenomic observations by Triggers et al. At David Good, laboratory in Australia, and until recently in bioarchive. So next slide, please. So in this atavistic theory of cancer, the genes that have appeared in the developmental multicellularity are precisely those that are altered in cancer. And this also has been observed by colleagues of mine about acute myeloblastic leukemia, but unfortunately, they were not sensitive to my point of view. But they have observed that the genes in evolution order in fresh blood samples from leukemic patients, the genes that were first modified were first of epigenetic control, then of cell differentiation and division of work, and finally only of proliferation and contact inhibition. That is in a reverse order. It is exactly what may be thought of as a sort of different construction of stories in a rocket. First, proliferation and contact inhibition, then cell differentiation and division of work, and finally, on top of this, epigenetic control on differentiation and proliferation. This is exactly the way that genes have been altered in this observation, observation in nature. And of course, attacking cancer on proliferation is precisely attacking where it's the most robust. So this is why attacking it by immunotherapy shows better results. Next slide, please. So let's go now to mathematics, and I will, for the present time, forget about biology, but try to document and argument my modeling with Frank, which is, as I said, it's a common work with Frank Ernesto Alvarez Borges. So the basic model for density of cells at time t with phenotype Z, and Z is in some domain in a multidimensional real space. It works in a non-local Lotka-Volterra setting in this way. It's a PDE, non-local PDE, and Lotka-Volterra type, where rho of t is the integral over the phenotype space of the whole population of cells. And here R and D are growth and death terms, which may depend on the phenotype. If one adds an advection term and a diffusion term, it runs this way, and this is a complete model. Here, V of Z is a real valued vector standing for, let's say, environmental pressure, unidirectional environmental pressure, for instance, induced by tumor environment modifications, such as drug infusion. And A is the diffusion matrix, which I will show you some slides later in precising, making more precise the model we have studied with Frank. So in this model, you can see heterogeneity in the between cell heterogeneity in the population. This is a cell population model. And you can see also the possibility of introducing plasticity insofar as the Z or the Z variable, it is a structure, continuous structure variable. It's not only a parameter. So it described as much as you want the plasticity and heterogeneity in the cell population according to needs of what you're observing in your cell population, especially if it's a cancer one. Next slide, please. So to comment about these terms, reaction terms, which are the terms that are not concerned by derivatives with respect to the phenotype structure variables. Reaction term may be diversely affected by external variables that represent the input from the cell environment, local or chemical densities, as I said. But when we want to, and this we have done in another presentation, in another article that was the subject of a collaboration with my former PhD student and now associate professor at Paris 5 Paris City University, Camille Pouchol. But there was no advection nor diffusion terms in this first work. Now, if you add advection terms, then you add a directional velocity, possibility to add a directional velocity, which is a way to understand plasticity as a speed of evolution due to some environmental pressure variable. And if you add a diffusion term, that is not the gradient as in advection terms, but this is a diffusion matrix, then these terms in the equations may be affected in a non-directional way by coding uncertainty in the phenotype, not directional way, by multiply or adding terms in this second order derivative way of considering plasticity. Next slide, please. So what is plasticity and how is it represented more precisely? As I said, I more or less said this in my previous words. Plasticity is what may be defined as uncertain the determination of phenotype, which may be in the diffusion term non-directional derivative with respect to phenotype term diffusion, but as insofar as it is related to speed of adaptation, it may be represented by the advection term, first order and directional. Biologically, it may be related to reversible, that is non-genetic, epigenetic nature, such as in a way that some people are maybe aware of this paper of 2010 in Cell, Sharma and O and other authors who showed us that in cancer cells also adaptation may be reversible, and it is continuous by nature because it is controlled by epigenetic enzyme activity. I must also stress that in physiology, such plasticity exists, and it is in a spectacular way represented by the possible ad integrum regeneration of the missing limb in the adult Mexican salamander axolotl. This is very spectacular. if you want to know what reversible adaptation can do, type axolotl on Google and you will see spectacular things about regeneration, tissue regeneration. In cancer, plasticity is very present because there is loss of organism control and cell differentiation. Dedifferentiation, redifferentiation, or transdifferentiation, as in EMT, that is epithelial to mesenchymal transition, which is tumor controlled and which is the first step in metastasis. All cancer cells have the possibility to develop phenotype plasticity and to resort to such capacities are fighting cancer drugs, for instance, by resistance, reversible drug resistance, and also by developing metastasis by the plasticity that cancer cell populations are endowed with. Next slide, please. So this, sorry for this slide, which is a bit dense, but this is the way by which we try to represent a phenotype divergence. And you can recognize here the main equation, but here we have tried to instance the trait, which is Z, that is X, Y, and theta. X is just to illustrate this, may be thought of as viability, that is way for cancer cell populations to resist some insult from the environment. Y is fecundity, that is a way to develop a potential of proliferation, and theta is the plasticity phenotype. And here you can see that it is in it's coded plasticity in the diffusion matrix, and whereas in the directional environmental pressure, it's coded by the V term, which is a gradient of pressure, unidirectional pressure from the environment. So what is D? D is the domain in which the phenotype evolves. And here, as you will see, we will consider it as a phenotype domain, which may be represented by this exterior of a disk in the square, 0, 1 squared. And the diffusion matrix, in fact, will depend only on theta, and it will, in fact, theta will affect only the X and Y term. We don't consider theta acting on theta, in fact, in this diffusion matrix setting. As regards the advection term, it's represented this way, and the total cell population is, as I said at the beginning, represented by this integral. Next slide, please. Yes, numerics have been represented in this way in simulations performed by Frank. In fact, we need in this PDE settings to have first function n0 of z at time 0, and here we have chosen this, and you will see the results of it in simulations. As I said, the D is the exterior of a disk in the square, and this is how the reaction terms looks like. This is how the diffusion matrix looks like. So theta is only, as I said, in the first part, in the xy part of the matrix. And the unidirectional advection term is represented here by this vector. It may include a theta or not. Next slide, please. So these are the simulations imposed by the gradient, the advection gradient, which is proportional to the current set of traits, xy, by being proportional to minus y minus x. So this is an illustration of the initial stages of the population density. You can see here the exterior, just 1/4 of the square, because the rest is the same. And you can see that initially the population is concentrated equally in x and y, and it's starting from theta at the 0.5 point. Then it acts like a cartoon. Then it will go this way by beginning of separation, and theta will be decreasing. That is, plasticity will be decreased. And going on, you will see that going on in time, plasticity still will decrease, and the separation of phenotypes will increase. And next slide, please. At the end, you will see that the phenotype theta is very low as compared with its initial values, and the two phenotypes are concentrated in two extreme values, making the population being constituted of two separated subpopulations, one concentrated around 0,1 and the other one on 1,0. In the two phenotypes, that is, one is privileging not the plasticity. The plasticity is diminished for all, but the viability phenotype, and the other subpopulation is privileging the fecundity phenotype. This is a way by, as you may have seen, by which we may represent in a PDE model phenotype divergence. And this has been published in this paper of Journal of Mathematical Biology in December 2022. Next slide, please. Now, what about cooperation? Well, Frank has designed a first simple prisoner's dilemma-like paradigm, which people who are familiar with the prisoner's dilemma will easily recognize. And you can see here at the bottom of the slide the classic payoff matrix of the prisoner's dilemma game. So there are two prisoners not communicating with each other, and they are submitted with the possibility to cooperate together, and that is betraying the other prisoner and cooperating with the administration, the jail administration. So if both prisoners cooperate, there is a benefit and a cost. So it will be B minus C if both prisoners cooperate, 0 for all, for both of them if both defect, and different consideration if I defect and the other cooperates, I will have benefit B, and I will have minus C if I cooperate and the other defects. So this is very classical, and we start in putting our populations in discrete time K, PK and QK, which are two cell populations supposed to represent cell populations in a discrete way, and we process in time from K to K plus 1 by this rule, which is indicated here. If there is cooperation in turn K, and if there is increase in cooperation, first line, and decrease in cooperation for the PK population, and the same if for the second population, the B population. Next slide, please. So, using the classical payoff matrix, we can have an expected gain, which may be represented in this way. It may be shown as being given by this relation. And if you try to make more precise the evolution from PK to PK QK to PK plus 1 QK plus 1, you obtain this rule of evolution and evolution of cooperation. In fact, it's related to Princeps papers by Axelrod and Hamilton, as some of you may know. And if this sequence of a limit defining such a line as function f1 and the other line as function f2, then if this sequence has a limit, it must satisfy this relation. That is, if at limit q and pq in time k, k going to infinity, it must satisfy this relation. Next slide. So it can be shown that, and this is in a paper that should soon be published, but it's available as a preprint on my web pages, and we can show that if this value, this is a key parameter E, which is dependent on the previous values epsilon ij. If E is negative, then there are only two possible steady states, and if E is possible, there are also only two possible steady states, one stable, one unstable, and these are opposites according to the sign of E. But if E is 0, then the only steady state is a unique solution of the equation, which is represented here, and which goes in this very simple equation, and it is a stable steady state. It's a homological function, so a very simple function, and it may be represented very simply. Next slide, please. And indeed, if you leave aside the expected average gain, there's some more work to be done on it, of course, but here we just show that with initial cooperation probabilities equally distributed, then cooperation probabilities with k going to infinity are given in this not surprising homological representation of the function q in function of p. So this is one thing we can show by this discrete time model. Next slide, please. But by analogy with this discrete model, at this point not formally derived from it, we can derive a toy PDE models. So we are closer to the initial model in as much as we have here a phenotype structured model, and here the phenotype is the probability, the continuous probability of cooperation in each population A and B. And we still have, as I showed you in the first slides of the mathematical setting, the total cell population mass, rho A and rho B, and the mean cooperation probabilities here are just this, as rho A tilde and y b tilde at time t. And we have global expected gains in each population, EA of t and EB of t, which were connected to EKA and EKB, which we have not studied in detail in the previous slide. And B and C are respectively the cost of cooperation and the benefit of cooperation in the classical and previous also discrete model of cooperation. Next slide, please. So in this way, we represent the two population densities by this advection, reaction advection equation. There's no diffusion in it so far. And you can see that here the advection terms in each population is represented by a derivative with respect to the continuous phenotype P here, and reaction is represented by GA and GB functions, which here we have chosen to set as in a simple way, which is from the point of view of the populations PB of the not the populations of the probabilities, the mean probabilities, PB tilde and PA tilde in an affine way. So gamma A and gamma B are here functions of the structure variable P that tune the non-local cooperation terms B PB tilde minus C PA tilde, and the same for B. So next slide, please. In this toy model, what can we obtain? And this is shown in the paper that should be soon published and which is available on my web pages as a so far only preprint, which would be augmented, of course, in the revised version. It is possible to show that by setting here PA star and PB star as the assumed 1 point singleton argument of the maximum of RA of P and RB of P in the support of NA0 and NAB0, which are the first that are related to the first time T0, which may be considered as a measure, in fact, not as a function. It can be shown that there occur these three cases, as in the case of the conclusion we had in the previous discrete model. If this parameter here is negative, then population A will go extinct. If it's positive, then the population A will blow up on a non-void internal I be included in 0, 1. Let us recall that here, of course, the structure, it's not a parameter, sorry for this term, it's a structure variable. It's a phenotype, continuous phenotype interval, which is non-void, and for all P in it, there will be a blow up of the total population. And the same is true for population B. So there is still much work to be performed on this model, but at least we have this rather spectacular and, as Frank said, dramatic sometimes effect of cooperations on the dynamics of the two populations. So this is, at this point, what we have achieved on these models of cooperation. And of course, there is much to be designed in the future. Next slide, please. So could we combine specialization, that is phenotype divergence, with cooperation in a PDE model? Well, at this step, we can just, and it remains to be done, but it's not so difficult to combine the two PDE models by identifying an A of P in the toy model with N of 0, 1, 0, 9 and P, P representing plasticity, and NB of P with N of 0, 9, 0, 1 P in the phenotype divergence model. This would mean that at an initially undivided cell population, we have first divergence in two phenotypes, and secondly only, that cooperation may emerge. But as I already mentioned to you, admitting that cooperation with division of works is what makes the real meaning of developing multicellularity in the deterministic body plan, then a project I have, in fact, with Emmanuel Trella at LGLL, Laboratoire Jaca-Lui Laionsà, is that we should optimize a global fitness variable, or maybe not necessarily only a fitness, but the production by cooperation of a common good, as in a sociological metaphor, relying on simultaneous growing specialization and cooperation in two complementary populations, at least first undivided and developing in specialization as time involves and specialization increases and cooperation parallelly. So we have to define and solve an optimization problem of global fitness or some production of a common good. And in our present view, this is the most challenging goal that we have to cope with from a mathematical point of view of optimization before considering the case of cheating cancer cells. Next slide, please. So this is in a short way, sort of conclusions I want to show you with possible consequences for cancer. There's, of course, a long time perspective involving modeling the body plan with its cohesion mechanisms, but much more observation, many more observation remain to be developed in understanding the body plan and its failures in cancer to understand it in a proper, maybe geometrical way. So, but only bit at the local tissue way, we need to explore and represent mechanistically the communication between gene regulatory networks that are at work in tissues, and this communication, which I mentioned to you as what I call the cohesion watch, are the ones that control local cell differentiations and proliferation that are impaired in all cancers. I mentioned to you local because all cancers start from local tissues. Cancer is never, as for instance, in other diseases generalized. I mean, for instance, neurodegenerative diseases that impair, or cardiovascular diseases that impair all the organism. In cancer, it's always a local beginning, which means that if maybe only locally we could have access to the messages that are impaired in cancer between tissues at a local level, then it could be possible to have access at a different way of understanding cancer. And genetic mechanisms in the body plan have been explored. So in the long-term view by Werner Müller, they both use the body plan term of evolution, of Darwinian evolution, and there have been also observations of cancer being observed as at very early stages of animal development, for instance, in hydra, in sponges, and in the more developed perception of the gene evolution by Eric Davidson and his colleagues, in the point of view of Darwinian evolution also, but in a very specified gene evolution of genes in echinoid mainly, but so far not from the development perception perspective of the alteration in cancer. Well, there are maybe some of you may be aware of the fact that local differentiation control has been mastered in very special diseases, that is acute promyelocytic leukemia, chronic myelogenous leukemia, which are due both to chromosomal translocation, that is molecular modifications inside cells, and acting by specified drugs on them. But can we change the focus from the cancer cells to the cancer tissue? This is a challenge. Also from the cancer point of view, exploiting clonal cooperation mechanisms in tumors have been hardly exploited so far and could be more documented to have access to acting impinging on cooperation mechanisms inside tumors. Next slide, please. Well, next slide. Next slide, please.
One more
Yeah,
next.
just one more. Yes,
Okay,
one.
we just skip this one.
Yes, one more, and after that it will be yes. Sorry, previous, then previous. But well, forget about the previous one. It was just mentioning that for the present time we can have different ways of acting on cancer by different models, but acting on cancer by this representation of phenotype divergence and cooperation models is still a big challenge. But I think that it's worth working, and there are open ways to work on it, be it from a biological and further cancer therapeutics, as I said, and this has been done in previous attempts. As I mentioned, this work with Camille Pouchol, and in another work on preparing the way to immunotherapy. But this is not a point of view of divergence, phenotypic divergence and cooperation in tumors. This is the previous and a parallel way that can always be developed. But what I would like you to, and next slide, final slide, please, Nastasia, is about such references that have fed our thinking about developing this model, and that I hope will feed also for the biologists and the cancer biologists in particular, and evolutionary biologists who might not be aware of all these references. And well, this is what I wanted to show you. And of course, I'm open to question now, and I hope that Anastasia will make this presentation available to everybody who will ask for it. Thank you all for your attention.
Yes, thank you very much, Jean, for this interesting and very dense presentation with many questions, both biological, mathematical, models. So there are many things to think about and to discuss. So I think that we have some time for questions and for comments, for discussion. So waiting maybe for other questions from our audience. I would like to ask, first of all, about, well, maybe kind of maybe technical question or concerning the model. I don't know what is the slide where the model is presented, but in the diffusion matrix A of, well, theta, in fact, it depends on theta. Oh, yes, this one, yes. For example, this one, yes. So you assume that diffusion coefficients depend on theta, on, yes, in your case, plasticity, but not, for example, on other variables, viability or fecundity. So why do you do this assumption?
Well, what you propose is possible, of course, but I think it's proceeding by how can this may be called, developing the questions by specialization in question. If you ask about diffusion, then you ask about uncertainty, non-directional uncertainty in the phenotype investigation, effects on the evolution of the population. If conversely you want to act on the directional effects of the phenotype environment, tumor environment, if you're in a tumor, then we should focus on the gradient. And next, if it's possible to have next slide, please. Yes, you can see here that, yes, this one, the numerics. Yes, we have here completely separated the effect of X, Y, which are on the gradient, that is on the speed of adaptation, and on the diffusion matrix, that is on the pure uncertainty on phenotype, which is not due to phenotype speed of adaptation. So of course we can mix all this, but here I think it wise to investigate separately plasticity and plasticity from the speed of adaptation point of view, and plasticity from the non-directional uncertainty point of view. This is why there is only theta in A and only index A and Y in V. I hope this answers your question.
Well, it's yes, maybe partially, because really it's well, some questions to think about, and also during your presentation and during the answer now, I paid attention that you presented from the point of view of phenotype and not genotype. I think that this is really a very profound question about the relation between them. So why you more think about phenotype and not genotype? So for you, all these changes happen as a small changes in phenotype, but not mutations. Not direct. Well, mutations can lead to these small changes eventually, but we don't know.
Of course,
it looks like in your model from the very beginning you just don't want to consider it from the point of view of genotype.
This is a question, in fact, that we will answer in the revised version of our article with Frank. In fact, if you're considering the Darwinian time of evolution of species, I do think that the phenotype adaptation comes first, but with time, which is very long in the Darwinian evolution, then you have time to develop after phenotype adaptation mutations, because phenotype adaptation is very costly. It involves epigenetic enzymes, so it involves a whole cell intracellular machinery of energy. And after some time, if it's too costly and you have the time to consider mutation, then comes a mutation which fixes the changes in the phenotype. On the time of cancer, it's different because the time is very short. It's a time, it's a lifetime or time of the cell population. And what is different is that there is genotype uncertainty. Genotype in cancer is very plastic. Not only phenotype is phenotype plastic, but also genotype and control, as I mentioned, control of proliferation. And this may due to, for instance, DNA since DNA what is doing well, some enzymes that control DNA synthesis during the G1 phase, and if the control at the G1 gating is not proper, then you have the possibilities to let pass in your cell cycle in cancer cells very already very deeply mutated cell, and this means that at the time scale of cancer cell populations, time is accelerated. Then you have not only phenotype plasticity, but also possibility of fixing it very fast by genotype plasticity. In this way, in cancer, I can say that both are phenotype and genotype are involved, because genotype fixation comes very fast because of the gene plasticity in cancer cell populations, whereas in the evolution, the Darwin evolution of species, first comes phenotype, but also genotype fixations, because there is no such thing as a genotype plasticity in short time, but in long time of evolution, of course, you have all the time needed to evolve in the body plan to fix these phenotype modifications. And I think it's a very important question. Time is important. Time of the time scale of the cell population in cancer is very short, whereas in evolution, the same phenomena may be at work, but the time is much longer, of course, billions of years.
Well, evolution can be much faster, not necessarily billions of years, but also at the level of several generations. But in fact, I think it's really interesting and long discussion, and I will try to make a really short comment, because when we started working on modeling of evolution with kind of models close to the models you consider, in fact, I didn't make a difference between, from the point of view, of the models, this, for example, X variable, what is X, phenotype or genotype? And for me, it was kind of more or less the same. I didn't really make a difference between them, of course, because I did not understand. However, last time, at least from the point of view of the evolution of biological species, I don't talk about cancer now, I come gradually to the conclusion that it's really a difference considering phenotype and genotype, and the models are different. And in our last work, we consider really it's in this evolution in the space of genotypes, not phenotypes, and even more. With these different models, we come to the conclusion that it cannot be described with phenotype. We really need to consider genotype. Why? Because, sorry to, well, I shouldn't be so long, but I think it might be interesting to discuss later. Making it short, if we talk about biological species, what is biological species? From the mathematical point of view, we can consider biological species as a stationary distribution, population density distribution with respect to what? Phenotype or genotype? Darwin introduced it.
It's a body plan. When you speak of a species, it's completely involved in the body plan of each cell of the multicellular animal. Sorry to have interrupted you.
But Darwin introduced biological species as according to their phenotype. So it's like we can consider as a sharp bell-shaped distribution with respect to phenotype. This is how Darwin introduced that. Now, if we study this question from the mathematical point of view, meaning that what is we should obtain this bell-shaped distribution as a stationary solution of some model. Because biological species exist. Let us take it as a starting point. Biological species exist. So then we need to suggest a mathematical model such that this bell-shaped distribution is a stationary solution of this model.
Yes.
Up to now, you agree with me. Then we consider different models, so distribution with respect to phenotypes and distribution with respect to genotypes. And if we consider it with respect to phenotypes, we don't have such solutions. I will stop now on that. I will send you some papers because I don't want to be long now because it's your talk. It's your talk, not mine. But I hope we can return to this discussion. Yes. So coming back, of course, to your results, because this is what we discuss today. One of the main results you presented today is about this phenotype divergence, and you explain that this divergence in two directions. One is related to viability and another to fecundity. But from the mathematical or modeling point of view, clearly this behavior is determined by, I think, two functions, R of z and V of z, because you take d of z equal constant. So now you have R of z, which is written here, and V of z, which is given below. But like looking at these formulas, it's a little bit difficult like that to understand how it works. So could you explain in simple words? So you have this, I suppose, kind of bell-shaped function for R. So a part of your solution converges to the maximum of this R, yes? And this which gives you one of them, viability or fecundity, and another part, another evolution of solution is related to advection. This is how it works.
And the def term, we have no information of it, so it's constant. As regards reaction term, yes, you can see that it doesn't involve plasticity in this setting, but one thing which makes the whole process work is the fact that, please, Anastasia, let us keep on the numerics. So next slide. Yes, here. you can see that there are two fixation points for the genotypes at 0109 and 0901, which means that we think that in the cell population, which has not been induced so far to diverge, there is just the same, the fact that there is some sort of, how should I say, platonistic conception of fecundity and plasticity to illustrate. But for what I, to invoke Plato is not necessary maybe, but you can see it in the reaction term. So the whole thing works, I think, mainly because there are these two stationary points, 0109 and 0901 in XY. And if nothing happens, neither with respect to theta nor with respect to V, that is with respect to A and with respect to V, then the cell population will remain stable on the initial 0.25 phenotype. But if something is acted on the diffusion or on the more quickly on the advection way, that is on the fast way, then there will be this possibility of divergence on to these two stable points with respect to the XY phenotypes. So there is just the same, the how should I say, built-in possibility to have different phenotypes. That is the possibility to diverge, but it will not be induced to diverge if there is no diffusion and no advection.
Yes, so in fact, when I asked my question, I did not pay attention that in this function R written here, in fact, there are two maxima, right? There are two maxima in these 2 points, 0109, 0901. There are two of them. So this is where your solution, well, evolve, right, to these 2 points. And of course, you need, for example, diffusion to
at least diffusion. Yes. That will diffusion only. It will be
yes. Diffusion with, if you have diffusion with respect to X and Y, then it will go to these 2 points, right?
But as you see, yes, the diffusion matrix, does it impinge on X and Y?
So there is no diffusion at all with respect to, because it is okay. So it's completely, so you have zero diffusion in the direction of X and Y, right?
And yes, in another model we designed with Tommaso Lorenzi and published in Cancer Research in 2015, we obtained that diffusion was mandatory to obtain such divergence. But if you have also advection, then it goes much faster.
Yes, but in this case you have zero diffusion with respect to X and Y. But you have this convection or advection term. But in which direction it goes?
But yes, you say no diffusion with respect to X and Y. I think I disagree, because in this diffusion matrix, you can see that the theta term impinges on the gradient term X in X and Y. So yes, this is a diffusion matrix, so it exerts on the gradient.
Okay. In fact, there is dependence. There is dependence of the diffusion coefficient on theta, but in fact, you have diffusion with respect to all variables, right?
Yes.
Yes. Okay. I see. Yes, I
more
see.
Specialized in this way.
Yes, I see that. Okay. Well, of course, there are many other questions. I'm not sure that we should have a very long discussion. In particular, also interesting question about cooperation. So how it happens that cooperations leads to blow up, and when it is blow up with respect to one variable, does it mean extinction with respect to another variable?
So far, with Frank, we have observed it separately, not trying to put things together. But as I
mean, sorry,
yes,
but
does one population explode and the other one goes to extinction? In the discrete model, maybe, but not in the toy model. In the toy model, it was completely separate. We just observed that extinction or blow up was possible in each population, not relating it to each other. But
yeah, but they're somehow coupled, I suppose.
I don't know. Maybe Frank could have ideas on this point, but I think that we still have work to do to answer this point. And well, if we include cooperation in the divergence model, then things may go in a different way, because we know, I meant sociological metaphors, that the best things, the best projects that work are always by cooperation between specialized teams. So why should it not be the same between cell lines? And in my point of view, I think that we could have much to learn from mathematics of cooperations in sociology, but I'm not aware of this field, unfortunately, so far.
Well, my last question is more biological. When you say about cooperation in cancer, I suppose there are examples, right, of cooperation of different cell lines, right?
Well, there's a striking Anastasia, can we go to the last slide with the references? A publication in the team of Cornelia Poliak. Is it mentioned here? Clearing. Yes, it's here. The Poliak and Marusik, but Poliak and Marusik, it's only a 2-page paper that sends the reader to the paper by Cleary, which is a 7-page paper in Nature Letters, which shows that in tumors with different subpopulations, which have been artificially selected as one subpopulation bearing gene A and not gene B, and another subpopulation bearing gene B and not gene A, when separately these subpopulations are led to evolve, they go to extinction separately, both of them. Mm-hmm. But when you put them together, and this has been observed in tumors, then the population will not go to extinct, it will proliferate. So at least there is a striking observation. I don't know if there have been as striking observation as this one, but it makes us hope that it's possible to block such cooperation mechanisms in tumors, provided, of course, that we don't block cooperation mechanisms in healthy cells. That might be a way to develop new therapeutic means. Well, this is an open way, I think, to new cancer therapeutics.
Yes, indeed, this is a very interesting question. So probably we should make a literature search on cell cooperation in tumors. I think it's interesting. So thank you very much, Jean, again, for your presentation. It's really it's really inspiring. It makes us think about all these questions. So thanks again. And since there are no other questions, we finish our seminar today. Have a good day. Goodbye.
Thank you all.
Thank you very much. Goodbye.
Thank you.
Bye-bye. Thank you. Thanks all the audience.